Welcome to Lesson 10 of Chapter 3 in Algebra 2. This is finding zeros of polynomial functions. On this particular lesson, what we do is we go three different ways of finding zeros, and a couple of them are really easy and you know them. And then there's one that's a little more challenging, but I think that you'll be able to get it pretty quickly. On the first one, using the binomial theorem, if you look here, you should notice that this is a 1, 3, 3, 1. If we just write those coefficients and take a second to look at them, if you're here for Chapter 7, Lesson 7 of this chapter, then you were exposed to the Pascal's triangle. And Pascal's triangle is a really neat little tool that we can use where Pascal actually developed this pattern where he would go 1, 1, 1, and then he went 1, 2, 1, and then 1, 3, because those two add up to be 3, and those two add up to be 3, and 1. And we would call this row 3, where we have that pattern, 1, 3, 3, 1. So that's how it is related to Pascal's triangle. That's what you'd fill in. You can even draw a Pascal's triangle up there. And that's called row 3 of the triangle. And what it shows is what the exponents, or actually what the coefficients are, on a binomial being cubed. So if we have a plus b cubed, we get 1a cubed, 3a squared b, 3ab squared, and 1b cubed. So we have these in our coefficients. And then we talked in Lesson 7 how to find the exponents of these. So definitely go back and study that one if you're not familiar with this. Okay, the next thing, use the binomial expansion to rewrite the function in the form of a plus b to the n. Well, we notice that the b value out here is 1 because b cubed is 1, so we know that the b value must be 1. The a value must be x because it's x cubed, so there we go. Now, having had that, we can identify the zeros of the function because x plus 1 equals 0 when x equals -1. Subtract a 1 from each side. When you have that, then you know that your 0 is at -1. So what we're saying is that on the graph of this function, at -1 for the x is where this graph crosses. Okay? How many times does each 0 occur? Well, we only have the one 0. It's occurring 3 times due to that exponent. So we would say 3 times. Okay, so the 0 of f of x is -1. The factored form of f of the x is x plus 1 cubed. Okay, can you always use the binomial theorem in this way to find the zeros of polynomial functions? I wish we always could, but the only time that we can is when we happen to see that the coefficients fit into Pascal's triangle. Okay, it's a really nice way, and you will see it on your final for sure. You will see it on the test for sure. So make sure that you have Pascal's triangle in your notes, in some notes for the test, so that you can look over at it and see, hey, does it fit on a row? Without actually graphing, describe the graph of f of x. Well, we know that it's cubic. So we know the end behavior. First we should say it's positive cubic. Sorry about that. So positive cubic. So that should tell us the end behavior goes up this way and down that way. So as x approaches infinity, going out this way, the y is going up forever, so f of x approaches positive infinity as well. Now as x approaches negative infinity, y coming down approaches negative infinity. We've already talked about that with odd functions. Okay, it is S-shaped. You might add that. I'd like to see that as a note. And I think the only other thing would be to tell me that the vertex is at that -1, 0. And maybe the translation from the parent function is 1 to the left. Now make sure that that fits with your equation. It says +1, so that certainly does fit with the equation. Okay, so that's the first way you can find zeros. Now, the next way to find zeros, sorry, I've got to put a line up on the outside of the, I got to just keep track of how low the camera goes. I can't see it easily from where I'm sitting. Okay, so the next way to find zeros is using the rational zero theorem. This one is not tough. Just remember how to divide polynomials, and I think that it'll be pretty easy. What we do is we look at the integer factors for the constant term. Here's your constant term. So the constant being the one without the x, you can make a note of that. The factors would be 1 and 2, so a plus or minus 1, plus or minus 2. Then we look at the integer factors for the leading coefficient. The leading coefficient's 1, so it's just plus or minus 1. By the rational zero theorem, the possible rational zeros are the number of constant zeros over the leading coefficient zeros. Okay, so you take your constant plus or minus 1 over plus or minus 1, that'll still be plus or minus 1, plus or minus 2 over plus or minus 1, so that would be plus or minus 2 as well. Okay, that's just something you have to remember. You can take the factors of this over the factors of that to get all your possible zeros. Those are your possible rational zeros. It's not all of them. Okay, so now the function has one rational zero, which is, use synthetic substitution to test each possible rational zero to identify any actual rational zeros. Okay, so we just need to test it. I'm assuming that they put this here for us to test with. Remember, you would take your coefficient off your x cubed, coefficient off your x squared, coefficient off your x, and coefficient off your x to the 0. That would be to the first. So you just go down in order. If there's only one, I don't know what for sure it'll be. I would just try 1. We might get lucky with that. Otherwise, we'll write up in here and we'll get more options. So synthetic division, remember, drop the first one down. 1 times 1 is 1. Negative 1 plus 1 is 0. 1 times 0 is 0. Negative 2 plus 0 is negative 2. 1 times negative 2 is negative 2. Bingo, we hit our factor. The way we know that is that it's a factor if the remainder is 0. So now we say the function has one rational zero, which is 1. So x minus 1 is the factor of g of x. Okay, use synthetic division to identify the other factors of the polynomial. Divide x minus 1 and complete the synthetic division at the right. So we did that, and we have 1x squared, because we go down, when we've divided, we go down 1 degree. So 1x squared plus 0x minus 2. We just brought these over and filled them in. Right as a product of two factors. So we have x minus 1 and x squared minus 2. We'll just drop that 0. The zeros of the quadratic function are, okay, Let's go ahead and figure out these others. We've got 1. We know that that's 1 because x minus 1 equals 0. Get x alone, we would have x equals 1. Now x squared minus 2 equals 0. We would add 2 to each side, we'd have x squared equals 2. Now take the square root of each side, we would have x equals plus or minus square root 2. Okay, so did you notice? We have 1, 2, 3 zeros, and this has to do with our last lesson, and the highest degree is 3. So kind of cool to see those old things coming into play here. Okay, write the quadratic factor as a product of 2 linear factors. Okay, so they want us to take this quadratic and break it down. Remember your conjugates, wipe out your middle term. So we can go x and x to get that x squared. And we would go radical 2 and radical 2 to multiply and get 2. And we need to do the plus and the minus to get rid of your middle term. Identify the zeros of the function. Well, now we know that they are 1, positive radical 2, and negative radical 2. Write the function in factored form. X minus 1, x minus radical 2, and x plus radical 2. Okay? So that's the way to do it if you can't spot any kind of a special polynomial here, or if it doesn't follow the pattern of the Pascal's triangle. We will be practicing that in class. Please don't miss class. Okay? When you use the rational zero theorem, did your list of possible zeros include the actual zeros of gx? Why or why not? No. The rational zero theorem only shows the rational zeros. You can write that. It only shows the rational zeros. So the only one from the rational zero theorem that we could use was the 1 because it's a rational number. These irrational numbers would not show up. We can't use them in synthetic division. How can you check that you wrote the factored form gx correctly? By multiplying the binomial factors. Okay? Sorry about the phone ringing. I'm going to just keep going. I'll answer it later. Okay. Rewrite the function as a special product. Okay, look here. This is using special products to find zeros. On this one, this is a perfect square, this is a perfect square, and we have a difference. So again, we look at conjugates to wipe out the middle term. Take the square root of x to the fourth, that would be x squared. Square root of 16 would be 4. And so we've just factored that. Okay? The next thing that you do is you would factor down the polynomial. Well, we did that. X squared minus 4. Oh, I guess you were supposed to say that that was a difference of 2 squares. Sorry. I have trouble filling in their blanks sometimes, as you guys know. Okay. Now, to find the zeros, all we do is we set each of these to 0. So we have x plus 4 equals 0, x minus 4 equals 0. We'd subtract 4 from each side. We'd add 4 to each side. We'd get x squared equals negative 4, x squared equals positive 4. Take the square root of x squared, and we get plus or minus square root of negative 4. Plus or minus square root of 4. Now, we have to take the negative out as an I. Take the square root of 4 and we get 2. Take the square root of 4, we get 2. Okay? Identify the zeros of the function. Well, this means that we could have zeros at plus or minus 2i or plus or minus 2. Zeros are what you get out of your factored formats. Write the function in factored form. It would be plus or minus 2i. Plus 2i, minus 2i, plus 2, and minus 2. How many x-intercepts does the graph hx have? And what are they? Explain what you know. Okay, they're going to have 2 real intercepts. Hopefully you recognized these are imaginary. Okay, So these are the only two that are graphable. So you might make a note there. The real intercepts are the only ones that will be graphable. Show how you can check the imaginary zeros. Well, we can multiply. We can multiply these back together to get the exact answer. Okay? In general, how many zeros does the function x4 minus a, x to the fourth minus a have when a is a positive integer? And what are the zeros? Well, up here we had that situation, and we found that there were 4 zeros, 2 real zeros, 2 imaginary zeros. And then what are the zeros? It would be the 4th root of a, plus or minus, and the imaginary 4th root of a, plus or minus. And you can just write that in there. Could you use the method of the example to find zeros of x to the fourth plus 16? Explain. Yes, we could. It's just that you would end up with more imaginary, because as you bring that 16 across, it's already a negative 16. And so you'd have the 4th root of a negative 16. But you could still come up with your roots that way. The main thing is on these is that it's a special product. In other words, we have a special method of how we can break it down and factor it. Okay? Last page of notes here. You'll come into class to do the practice. This is going back to the very front one, the one that looked like the Pascal's triangle. It shows that it was a 3rd degree. And remember that it was x plus 1, which made it x minus 1 to the 3rd. That means that it occurs 3 times, so the number of zeros was 3. On the next one, we had to do the rational, what is it called? The rational zero theorem. Sorry, it blanked out of my head. The rational zero theorem, where we divided the factors of the constant by the factors of the leading coefficient. And we found that we had 3 zeros. Again, they were the 1, the radical 2, and the negative radical 2. And it's 3rd degree. 4th degree. We broke this down, and look, how many zeros we found? 4. So we've talked about that in class before, is that this indicates how many zeros. Okay? So how does the quadratic formula prove the fundamental theorem of algebra for the case N2? Well, this is pretty cool actually, guys, because it takes us back to a couple chapters ago when we were looking just at quadratics. And remember, I had to look at those discriminants. So we had radical b squared minus 4ac. And when you did that, remember, if you got a positive amount in there, if it was greater than 0, and we shouldn't do the radical around it, but if you got greater than 0, then we knew that there were 2 real zeros. And if you went to the graph, it would draw out like this, where it was crossing in 2 spots. Remember that? And if we did b squared minus 4ac, and it was less than 0, we always ended up with 2 imaginary zeros. And remember, you could solve it algebraically and get those, and they would always have the imaginary number with them, just like we did previous in this unit on the x to the fourth minus 16. And when we graphed, it wouldn't show them because they were imaginary, but we knew that there were 2 imaginary zeros. Now, here's the cool thing. When it equaled 0, 4 minus ac equaled 0, it looked as though it was 1 root, but it was plus or minus 0, which is only 1 point. But do you notice how it no longer crosses? It's tangent. And remember what we've learned about the tangent zeros. They're still occurring twice in order to be tangent and to not pass through. So I just think that that's so awesome. Last thing here. Whoops, didn't mean to kick the camera in my excitement. Okay, the last thing here. If you apply the fundamental theorem of algebra to any polynomial function, you can conclude that f of x has one complex zero, z1. So by the factor of theorem, x minus z1 is the factor of f of x. This means x minus z1 times qx, where qx1 is a polynomial whose degree is 1 degree less than f of x. Explain how you can, so basically what they're saying, in case that got you confused, is back here we did it, right here. When we divided by the x minus 1, and we got the answer and this was 1 degree less, then we could go to this and say that it was x minus 1 times what we got here, which was x squared minus 2. Okay, so that's all the more that they're saying, but they want us to explain how you can use this idea and repeatedly apply the fundamental theorem of algebra to prove the corollary of this theorem. Okay, so we're wanting to do a proof again, so we might go f of x, they just said that it's a factor of x1 minus, or just x minus z1 times q1 times x. So if we look at that, then we could say, okay, we know that this is 1 less than that. So if we went again and we said, well, now we end up with 2 factors. Now we're up to at least the x squared there, so we would have another factor here indicating that growth. And basically what we're doing is we're saying that q of x equals f of x times n minus 1. So whatever factor we pulled out, it's going to be 1 degree less than this one is. This q of x would have to be the f of x n minus 2 because we've pulled 2 factors out. And you could keep going with that. You could have 3 factors pulled out and go q of x equals f of x n minus 3. This always has to drop down each time that you get an answer in synthetic division. It's dropped down 1 degree from what you were dividing by. Okay, can you conclude that x to the 5th minus 4x squared plus 1 over x has 5 zeros? Why or why not? Unfortunately, no, we can't conclude 5 zeros. I know that you'd like to because that 5 right there, but be really careful of this. That's not a polynomial. That's a rational function. Okay, so be aware, watch for that on the finals, watch for that in future tests, in future situations. That's a rational function. We can't apply these theorems that we have for polynomials to rational functions. Okay, tomorrow in class we will work on these practice problems. Hope you enjoyed that. We'll see you in class.